This video will start a series of instructional videos for chemical engineering brought to you by the Zeta chapter of Omega Chi Epsilon at Purdue University. Over the course of the next 4 videos, we're going to cover a wide range of math topics relevant to chemical engineering courses. This will set us up with a mathematical foundation for the various topics that we will cover for courses such as fluid mechanics, heat and mass transfer, statistics, and process controls. The topics that we will cover in this video include notation, coordinate systems, and an introduction to vectors, tensors, and their operations. The next 3 videos will further cover vector-tensor operations, vector-tensor calculus, simple ordinary differential equations, boundary conditions, and Laplace transforms and partial fraction decompositions. Please note that while these topics will be reviewed, certain specifics and details may be left out as our primary objective is to address where students may struggle the most. Let's start with notation. Note that preferred notation will differ between professors and textbooks. This is just the notation that we will use for various segments of this video series. Beginning with notation for mass and energy balances, we will define m dot for mass flow rates, n dot for molar flow rates, carets or subscript s will denote mass basis, tilde or subscript m will denote molar basis, capital letters will denote material or energy flow, with lowercase letters denoting material or energy flux, such as capital Q for heat flow and lowercase q for heat flux. Constants and subscripts will be defined on a case-by-case basis. Most chemical engineering problems will take place in one of 3 coordinate systems: Cartesian, cylindrical, or spherical. Really, you can choose any coordinate system that makes the problem most convenient to solve, and in most cases, this will become obvious based on the geometry given in the problem. For example, you may choose to use cylindrical coordinates for problems involving tubes and pipes. Cartesian coordinates involve 3 translational directions x, y, z. Cylindrical coordinates involve 2 translational directions, rho, z, and 1 angular direction, theta. And finally, spherical coordinates involve 1 translational direction, r, and 2 angular directions, theta and phi. Please note that r can be used instead of rho for cylindrical coordinates and vice versa for spherical coordinates. It all comes down to how the professor and or the textbook defines the radial variable. Similarly, in spherical coordinates, theta and phi may be defined interchangeably. Do make note of how they are defined for each course. Usually the textbook's appendix will show how they define each variable. Let's do a review of vectors and tensors. If you are coming fresh out of Calc 3, this will be a useful review of vectors and introduction to tensors to help you along the way. The purpose of this review is to give a conceptual understanding of certain math topics. Use the ideas presented here as an opportunity to possibly think about vectors and tensors with a little more depth so that it makes using the concepts in real problems easier. So consider the idea that a vector is essentially a scalar to which we have assigned directionality. Whether we represent this directionality with x, y, z, or rho, theta, z, or r, theta, phi, however we represent the directionality, in the end we are associating a number with a direction in space. Vectors essentially add 1 layer of complexity to scalars. The same can be said for when we go from vectors to tensors. When going from a vector to a tensor, we are merely adding 1 more direction to the mix. So while a vector is a scalar with 1 direction, a tensor is a scalar with 2 directions. Tensors become especially important when dealing with fluid transport because we typically find it of interest. For example, let's draw a pipe. So this is a section of a pipe, and let's say we have a fluid flowing through that pipe towards the right. So we have a fluid flowing towards the right, and we typically find it of interest to study how the momentum in the fluid's motion, which say the fluid's motion is in the z direction. So we may find it of interest to see how this momentum, right, so this fluid is moving with a certain momentum, and how this fluid imparts a force on the fluid surrounding it due to its motion, and how that fluid imparts a force on the fluid surrounding it. And eventually, this propagates through and through, and we may find it of interest, for example, to determine the force on the walls of the pipe. And as you'll see, there is going to be a force in the z direction and a force in the r direction. And so essentially there's a z component of the force that is due to the shear stress imparted by the movement of the fluid in the z direction, and the r component of the force is due to the normal pressure associated with the fluid. And so since we are dealing with two directions in this situation, z and r, z being the direction of fluid motion and r being the direction in which momentum is being propagated, we require tensors. And if you have taken fluid mechanics already, you will recall that this requires us to resolve the RZ component of the viscous stress tensor tau. Alright, so let's get started with a recap of vectors. We can write vectors in terms of components in each of the 3 dimensions of the chosen coordinate system. Let's work in Cartesian coordinates for simplicity's sake. So here I will write a vector in terms of its components, with ax representing the x component, ay representing the y component, and a z component corresponding to the z component. Ex hat, ey hat, and ez hat will represent the unit vectors in the x, y, and z directions respectively. And so note that these unit vectors are all perpendicular or orthogonal to each other. So let me just show that visually. So you have ex hat is the unit vector in the x direction, ey hat, ez hat in the y and z directions, and all of these are orthogonal to each other. Alright, so we can also write this vector as such, so ax, ay, az, in order to just save some writing. Alright, so these are the ways we will denote vectors. Analogically, we can denote tensors in a similar way. So we can write axx as our component, with our directions being ex hat and ex hat, right? 2 directions, plus axy, x hat, ey hat, and this will continue on, and we'll have 9 terms in total, our last one being azz, with our directions being ez hat and ez hat. We can also write this as a matrix, so we'll write a matrix with 9 components, and we can just write here axx, axy, axz, ayx, ayy, ayz, azx, azy, and finally azz. So let's talk about the dot product, which is a very common math operation that comes up with vectors and tensors. Dot products should be recalled as an operation that can be defined as following. When we perform the dot product between 2 same unit vectors, so ex hat dot ex hat, or ey hat dot ey hat, or ez hat dot ez hat, the result is equal to 1. Right, so let's box this up. And so by definition of the dot product, when we perform the dot product between 2 of the same unit vectors, the result is 1, so of the dot product. So meanwhile, if we performed the dot product between 2 orthogonal unit vectors in not the same direction, so ex hat dot ey hat, so that'll be 0. and or EY hat dot EX hat, or EX hat dot EZ hat, for example, and so on and so forth. So EX hat, that's an X, dot EZ hat equals 0, and so on and so forth. So if we were to perform a dot product between two arbitrary vectors, so let's just say 3 EX hat plus 2 EY hat plus 5 EZ hat, and we dot this vector with another vector, say let's say 4 EX hat minus 5 EY hat plus 5 EZ hat. Right, so you would the first step would be to distribute as you would for normal multiplication. So we distribute that, and essentially we do that a total of 9 times. Obviously, when you do this, you would probably skip a lot of these steps. I'll just show very thoroughly what's going on. So let's write down the first term. So the first term is just 3 EX hat dotted with 4 EX hat. I'll write down a couple more terms just to show the process. 3 EX hat dotted with minus 5 EY hat, and so on, and you'll have 9 terms in the end. So the first thing we'll do is we'll pull out the numerical values out to the front. So 3 times 4 we can put it at the front, and then in the back we'll have EX hat dotted with EX hat as a dot product operation is done between vectors, right? So we can pull out the numbers in the front, and then we'll just deal with the unit vectors when we do the dot product. So and so on, and 9 terms as we've defined before. EX hat dot EY hat, that's just 0, so this one is just 0. But EX hat dot EX hat, that's 1, so we can say that this is 1, and so this term will reduce down to 3 times 4, and we'll end up with essentially pulling out all the terms where the unit vectors are the same. So for the y direction, EY hat dot EY hat, you'll have 2 times minus 5, and then for the z, we'll have 5 times 5, and then the rest is just easy math. The answer then is 27. So the thing to note here is that you are left with the following. So we're left with a scalar value, right? 27, without direction. So remember, the dot operation removes directionality by replacing the dotted unit vectors with either 1 or 0. That's why we are left with a scalar value. We started with vectors, we're ending with a scalar. This ends the first of 4 videos that will cover various math topics relevant to chemical engineering. The next video will continue by showing an example of dot product between a vector and a tensor, and a double dot product between 2 tensors, and will cover some vector and tensor calculus operations as well. See you in the next video.